Okay, so hello everyone, welcome to this Le Material reading group session. And today we have Luca presenting this paper on sampling of transition states using diffusion. So the floor is yours, Luca.
All right, thanks. So thank you, Hali, and thank you, Louis, for inviting me. Today I'll be presenting some work I did when I was visiting Rafa's group at MIT, alongside my co-authors, so Hyukjun, who was the lead on that, Sujung as well, and Miguel Yongxi, and of course Rafa. So the topic of the talk today is the a priori sampling of transition state with guided diffusion. So first, I want to make sure that we are all on the same page regarding what we call transition states and why they are very important in chemistry. So first, transition state, as you can see on the figure, can you see my, yeah, you can, on the figure on the bottom left here, it's just defined as essentially a first order saddle point on the potential energy surface. So essentially this determines the rates of a chemical reactions, because when you go from a reactant to a product, you have to cross this barrier of minimum energy path, and this defines your activation energies. And using something like Arrhenius laws, you can derive kinetic rates, which is key to characterize any chemical reactions which are kinetically limited processes. But the problem is that computationally it's very expensive to sample, because if you would just run, for example, MD simulations, you will have to wait for a very long time. For example, run for seconds or milliseconds, which is today computationally intractable to do. And so therefore people have come up with essentially two sort of ways to sample these rare events. So first, the kind of simulation-based or time-dependent transition state search methods, which are essentially about biasing your simulation. So you still run the MD simulation that otherwise would be intractable if you want to sample the transition state, but here you're biasing the simulation. For example, a typical thing that people do is using metadynamics, where you iteratively add some bias potential, and you essentially float the PS until you cross the barrier. Then after that, you can just reweight your ensembles or ensemble of configurations, and get the free energy surface. And the problem here is that it's still relatively expensive to do, even though it's much more tractable than just running blind MD. And the other problem is that in order to bias the system, you need to define what we call a collective variable, so a CV, which is essentially about defining what are the degrees of freedom for your system to evolve during the chemical reactions. And the second kind of method is a kind of time-independent transition state search. So whether that's single-ended methods like a dimer, for example, where you just optimize your sample, like you optimize a single structure to go to the saddle point, or you can use also, like as pictured here, double-ended methods like NEB, where you have to interpolate a path and then you optimize the whole path in order to converge to the transition state and get a good transition state guess. But the problem here as well is that, as you can see below, for this alanine dipeptide example, if you want to sample all three transition states, you need to kind of already know that they are here, because you need to have an initial interpolation that's already close enough to the transition in order to not completely mode collapse onto a single transition. And therefore, in both cases, we can see that the main problem is that you still require heuristics each time to manage to find the transition state, which is a strong limitation for coming up with a method that's just general and can work out of the box in a very systematic way. And so that's what's, yeah.
So for MLIPs, is like the linear path the most commonly used, or
here I think I showed geodesic interpolations. I think it's mainly about like physical validity here. If you would show the linear path, it would be a bit more linear. But this is just a projection. The problem here is that if you use a linear path, you just don't converge anything because there's just atom clashes and it's horrible.
So it's usually a bad practice to do the
I guess it depends on the structure. I would say for materials, for example, you may have structures that are not like that are relatively safe to interpolate. But here, when you have like lots of torsions and degrees of freedom that may overlap when you just interpolate them linearly, I would say that's quite dangerous.
And other naive question. So for the first technique, is it like you just have a bunch of initial points and then you run MD on them and you hope that some
for example, for metadynamics or like OPS metadynamics, you basically define the one or two collective variable, which will define the coordinates where you put your bias potential. So here, and then you just start from one point, your MD, and then as you go, you build the potential. And then the idea is that the system will not visit the part of the PS that's already sampled thanks to that bias. But yeah, you start essentially, I mean, you can, I guess, start from both end state as well. It depends on what you're modeling. So yeah, so because we don't want heuristics, we defined our problem as follows for the method that we're gonna present. So we want to sample transition states with no prior knowledge of the PS, so no CV or any kind of intuition. We also assume that we have access to limited data. And so we will assume that we have access to 2 short MD simulations launched from the reactants and the product basins. And of course, because the PS is a force field relative, force field dependent, we assume that we have a force field to characterize the PS in the first place. So here is a broad overview of ASTRA. And then I will dive in a bit more detail into each one of these steps. But essentially, the first step is that you trained a conditional model. So you have your 2 states, your reactant and product, for example. And then, so let's call it state A and state B. And then the first thing you do is that you trained a diffusion model condition on state A and B. So that's the diffusion model is able to sample the distribution that you run through your 2 MD simulations. The second step is to get an initial kind of guess of the transition state on ensemble, and you do that by using score-based interpolation inference-time steering, which is essentially here. What we use is the sampling of the isotensity surface between the 2 conditional models, and we assume that it's like kind of good prior to sample a region that's close enough to the transition state, but also broad enough so that we don't mode collapse. And the next step is to refine the guesses from step 2. And to do that, we will use basically an adaptation of a typical transition state optimization method where we just approximate the reaction coordinate by the difference of scores, and that will turn out to be very efficient and robust. So to give a bit more context into these points, the first piece of background that's important is inference-time steering for diffusion models. So the idea behind generative models is essentially just learn the training data distribution. So for example, you can have a distribution A and a distribution B. And the idea is that what you do is that you train a model that's able to sample A and another model that's able to sample B. this is the QT of X, this distribution. And how you do that is that you learn these scores here that you parameterize by neural net. And then at inference, you can just run an SDE ensemble from the target distribution. But what if you don't want to sample this exact QT of X? And then the idea is to use these inference-time steering techniques to bias the sampling towards different target distribution. And the specific example that we use is the superposition of diffusion models. So SuperDiff here, where the idea is to sample the kind of equal density regions under the two model A and B. And you do that by enforcing along the SC this condition here. And what the authors derive is simply that if you want to sample this equal density region, you have to extrapolate the scores of the model A and the model B. And just what determines that you're on the good surface here is this kappa factor, which is obtained from a relatively simple set of linear equations based on this condition. The other piece of background for step 3 of our method is transition state optimization. So essentially, the idea of transition state optimization can be summarized through this kind of equation here, where F denotes the direction that you use to move your structure towards the saddle point. And the idea is pretty intuitive here. U is the energy. So essentially what you do is that let's say you are at some point in red here. What you do is that you move down one time along the gradient of U, so essentially a fourth step. And then you move 2 times along the gradient of U, but projected on the reaction coordinate, which is the coordinate that's bridging your two energy wells. And that effectively does is that you basically, in fact, move down in all direction, except the direction of ascent, which is the reaction coordinate direction. And that makes you converge to the saddle. And in fact, that's essentially what, for example, the method that we're going to use to characterize the saddle point use, the timer method. And each time, the main question is essentially how do you approximate this reaction coordinate without having to compute the Hessian, because that's pretty expensive.
How is the reaction coordinate? Is it like the difference between the two?
So the reaction coordinate is like what, like the true reaction coordinate is what defines the minimum energy path. So whatever's combination of coordinates on your high dimensional surface that defines the going from one end of the one valley to the other valley, essentially. Yeah. And that's the thing that we're trying to approximate. So yeah, now I'm going to dive a bit more into each of the step 2 and 3. So first, the score-based interpolation gives you the initial guess. So what we do in practice is that we define again state A and state B that we obtain from running short MDs, and then we train our DDPM model with the classifier-free guidance. And then we sample the equal density region, and you can see on the right here what this essentially does. The green dots here correspond to sampling with these kind of score extrapolation, the DPM model condition on A and B. But you can see that it's still relatively far from the two saddles that are here. So then we need to refine them with a method that's actually finding the saddle points.
So if I understand correctly, you run 2 MDs on each state.
Yeah.
And get all these points, then you approximate these distributions.
Yeah, you learn the distribution with the generative model.
Using those distributions, you generate those samples using that.
Yes, exactly. Yeah. Oh, there's a question. Yeah. Luis?
How do you choose kappa in the previous one?
So essentially, it's you can find it on this paper here. it's derived from this
Oh,
condition
right.
here of being incongruency.
Right.
But so, yeah. All right, and then we use what we call score-aligned ascent, which is essentially using the exact same formula that I showed a few slides ago on how to optimize transition states. But the main thing here is that you use as an approximation of the reaction coordinate this difference of scores, and the assumption is that it will like kind of provide a rough but good approximation of a good ascent direction. And what you can see here on the right is essentially for these 2D surface example, how the true reaction coordinate in red agrees with the score difference that we use. So it's not exact, but we'll see that it's at least enough for how we use it. Yeah.
Sorry, maybe on the previous slide, one question. Yeah. So when you sample state A and B, that means that for every reactant product, you need to you need to generate 2 MD sets and train 2 diffusion models per reactant.
You essentially train one with classifier free guidance. So it's like one model that's able to condition on each state. So here I presented this as like you train one model for A, one model for B, but you can equally do that for just one model that's conditioned on A and the same model that's conditioned on B.
And what is the condition that you give it? Like what's...
You just label the samples. Like you said, you just say in your training data that all of these structures are state A and all of these are state B. And it's just generate the conditional distribution and not the like general distribution, essentially.
Then, but that still means that you need one diffusion model per system.
Yeah. Like how we set up the problem here is a single system approach.
Got it.
That's how we set up the problem.
Very simple question.
Yeah.
What do you mean by equal density region?
Essentially like a region where you have equal probability of being under model A at under model B. Like for example, if you're like around here, you're kind of equally probable to be from the model condition on A than the model condition on B.
And
that's like a rough prior for saying what's a good intermediate region from which we can start. And that's like broad enough.
How is that estimated? Is it like based on the energy of the potential energy surface? Or?
No, that's like based on the interpolations of scores.
Okay.
That's the kappa essentially. That defines how you find that. Okay, so yeah, so then we use this difference of scores to approximate the reaction coordinates, and then when we run the optimization with this ascent direction using the force field and our difference of scores, then we can just optimize to the exact saddle points. But still, and one interesting property again of the method is that because we use kind of broad initialization of transition state ensemble guesses with the score-based interpolation, so the first step from here, then it allows us, when you run SAA, to even when you have these like wildly different paths, then you can just like find the two paths without explicitly telling the model to look right or left. So it's really like a synergetic use of the two that allows you to sample things a priori.
When you have multiple saddle points.
Yeah. It's like a two path. There's like one path up and one path down, but you have no reason to sample to either than what you would obtain, which is, for example, NEB. You would like have to, unlike this climbing image NEB, you would have to relax, so you would be
closer to one.
And then you would be closer to one. You would basically collapse onto one. And then I guess it also depends on which method you use.
In that case, where you have more than 2 transition states, or is that what happened?
More than 2? Yeah, that's the case that I'm going to show in a few slides. But still, these are 2D potentials, so they are fairly easy to converge, and especially because like we have like the exact analytical PS in how we describe it, so it's like not very noisy, etc. So now we have to assess whether that works for a chemical system, because that's the true goal. And to do that, we first introduce the 2 kind of evaluations that we will perform to determine whether we are a transition state or not, essentially. So the first thing is to, yeah. Someone has a question. So it's able to find all the transitions state between 2 states without guessing. Essentially, yes, that's the idea. Because of like the broad initialization that you provided, and then the SIAs allows you to refine to the saddles in a quite robust way, regardless of the exact position of the SBI samples. So yeah, so the first evaluation that we do is a saddle point evaluation via timer. So essentially, the timer is this single-ended transition state optimization method that allows you to characterize the first order saddle points, because it's supposed to converge to these exact points. And so what we do is that we start from our transition state guess from our method, and we run timer optimization. We initialize it from a Hessian to make it more efficient. And then we compute a bunch of metrics to characterize how close we are to the actual saddle, which is so how close we are to the timer optimized structure. So we measure convergence rates, number of steps to converge, energy difference, and position differences. And then we also use a more dynamic approach to characterize the transition, which is the committer, Q of X. So the committer is essentially defined by the probability that a trajectory starting from state X will reach one metastable state before the other. And so the idea is that when you are at the transition, you are at committer Q equal 0.5, because you have equal probability when you start a simulation from there with random velocities to end up at either in either state A or state B. And so it leads to these kind of surfaces that you can see on the right here, where the 0.5 is the transition region. And one thing to note here maybe is also that this coincides with the first order saddle, given that you have a single dominant barrier, and also, of course, because here we're running simulations if you have small enough entropic contributions. All right, so the first result on chemical systems, we first used the alanine dipeptide system because it's interesting in the way that it has 3 transitions, and transitions that are like geometrically pretty distinct. And so it would be hard for a method that's agnostic of like human intuition to find them by itself. And so what we show here is first the SBI samples, and then the refined ASTRA samples that nicely converge. And we can see that in terms of committer value, we managed to converge to the 0.5 region, which is good. Oh yeah, and you can see in the blue and the coral here the training distribution. So there, like the model has no like knowledge of the transition states region at all.
Are you able to know the committer value?
So you sample the states here, and then you run like, I don't remember how many I run, but I run that, like, for example, 100 simulations, like Launchman dynamics simulations with random initial velocities from the Boltzmann distribution. And you just like label one trajectory as like either like 1 or 2 based on if you reach state A before state B.
So it's a function you can calculate based on the points you have, but you don't know it everywhere. You can
Yeah, I mean, you could build the surface if you would like sample the thing, but it's kind of it's yeah. All right. And then we also compute these dimer related metrics that you can see here. So we again take our ASTRA samples and then we run the dimer and we measure the number of iterations that you need, the position difference and the energy difference, and we can see that we are quite nicely distributed around like we need very few dimer iterations. We are very close to the initial structure, and we also have nice convergence rates. So that's pretty encouraging. But maybe the main thing that I want to stress out here is that we're able, thanks to this broad enough sampling from SBI, to converge to all three transitions when we run SAA, and we did that without putting any knowledge of where the paths should be. We just ran a blind MD from each state and train a model up on that. All right. So for the next chemical reaction, so before it was more like conformational dynamics, but it was still interesting because it was about like there was like three very different transitions, but now we wanted to test that also for like proper bond formation, and so we used these this donor acceptor Steinhaus adduct reaction, where we have like these cycles forming. For example, we have a schematic of the reaction that's at play here, and again. What we show here is the training distribution in blue and coral. Here we project in a CV space, which correspond to the degrees of freedom that are relevant for the chemical reaction at play here. And we reported the commuter value again. What you can observe is that the commuter is like much more, like the sampling is essentially less peaked around the commuter 0.5, which is notable. But what you also have to note here is that we're not actually using MD commuter based, like a commuter based on simulation. But what you can also do is use like a trained ML model to output the commuter based on your distribution. And what we use here is the training data and the commuter model from one paper, and therefore the like ML commuter will like describe something that's different from just running a commuter evaluation like what we did here, which is I would say a bit more coarse-grained. It's just that I think we didn't have the precise force field that they use for the data available, and so like it doesn't make any sense to evaluate transition states with a different force field because it's like force field dependent anyways. Okay, yes. But again, what's probably what's more important here is that when we look at the like structural diversity of the samples from our like SBI plus SAA method, is that we are able to capture pretty much all of the different kind of configurations or like approaches that you can have to like create the bond. And we evaluated that by running essentially a bunch of different like double-ended or single-ended transition state optimization method for that system to get like a kind of a broad set of possible saddle points. And you can see here that, for example, some of the method captures a certain cluster of structures, some of them capture another one. And what's interesting in that is that our method is able to pretty much cover all of the clusters. So that's the main feature of what we want to do, because we want to sample the TS ensemble in its full diversity without, again, heuristics. Do we have time for it? Yes, maybe I can pause a little here, and if you have any questions before I dive into a bit more as for the whys the method works and what makes it robust. So if you have any questions, I'm happy to take them now, and then can dive into a bit the rest. No questions?
I guess I do have a question.
Oh, yeah.
Very quick question. How long does it take to go from, like, say you have a reaction and you want to estimate those transition states? How approximately does it take to run the full pipeline?
Well, I don't know. It depends on the system. The thing is that the model that we use here was equiform V2, which is not very efficient, to be honest. So in terms of computational costs right now, it's like one of the main thing that you could easily improve.
So change the force field?
Yeah, just change. I mean, no, like changing the diffusion model that you run.
Oh,
Oh yeah. So sorry. The force field is a classical one.
Okay.
And also we use like standard DDPM sampling of all like 1000 steps. Because I think at the time there wasn't any ways to sample super diff from like, faster samplers, essentially, or we didn't take the time to think about that. So that would be also like, of course, it's like the two main thing that you could do to make the method way faster.
Do you know if using different force fields would help as well, or?
What do you mean different force?
Like using classical force field, or are there ways that if you use a more accurate force field, you get better transition states, or that's difficult to evaluate?
I think it's like, I would say that in the context of this paper, what transition state is accurate is force field centric. Like we evaluate if we are accurate with respect to what the force field can describe. But I mean, the question of is a force field accurate to describe certain transition is like a more global, I would say, computational chemistry problem, and it's not like dependent on what we do in our method.
Because there is a case where you might have a force field where, I mean, the potential energy is most of the places, but like maybe in the region where you have the saddle point or around it, you have a discontinuity or something.
Yeah, that's possible.
Like, is the method robust to that, or is that something you haven't?
I mean, I think we use two different kinds of force field. So I guess it's robust in that sense. But for example, one interesting thing that people could try is using, universal MLIPs. I guess it's the main way you could like expand that. Even though right now they're not like super accurate for transition, so that may be super noisy, as you were saying. So I guess there's no clear response to that yet, but we expect, given that what I'm going to say next is that it's like relatively robust anyways. Warnings to density of points. Yeah, I would say yes to your second sentence. Like it's very dependent on the initial sampling. I would say for example, like the third transition here, we get like very few points. Because when you look at the initialization, you just get very few points here, because the way the MD like was trained, like the first distribution was trained, is like not at all a lot of density here, so the model like struggles to sample here, if that makes sense. Okay, so all right. So next, to dive a bit more into what are we doing, because like basically I said that we're using score-based interpolation and then we're using SAA, but actually we're like not doing that. Like we're not just doing that, because like basically we made three observations that led us to come up with a way so that this method is like robust and can like sample structures that are like physically meaningful. The first observation is, of course, when you look at the difference of scores as a reaction coordinate, the difference with the true reaction coordinates is that well, the difference of scores has absolutely no reason to be physical, because the models are not trained on these intermediate regions at all, so they have no idea of what's physical in there. I mean, they still have the general priors of what's a bond, what's a torsion, I guess, but like the precise geometry will surely not be physical. And so you have a strong chance, and that's actually what we've observed, that SAA might push your configuration kind of out of the data manifold when you think of the PES as being the data manifold. And the second thing is that when you compute scores, and kind of I would say a general observation of the diffusion model field is that the scores are more reliable when you compute them slightly noised versus precisely at the clean data level. And so in that sense, it would be better to compute the SAA scores, so the reaction coordinates at some latent level and not directly on the data manifold. But then the question is that if you have all of these noise structure and then your SAA is pushing things out of the manifold, how do you have actually physical structures? And the answer to that is just, well, you just have already denoiser, like the DDPM model that you trained. And the idea is that you can use this model to actually correct for the unphysical artifacts that might arise from SAA dynamics. And so what we do in practice, what ASTRA is doing in practice is, so when we sample with score-based interpolation, we run the SDE, and then at some point before we get to the exact data manifold, so the clean data level, we pose the SDE. So we define that through a pose ratio. Then we optimize with SAA, and then we resume the SDE to kind of finish the denoising and have structures that are physically valid. And so to kind of characterize that, I want to show you these ablation studies that we did. So I would say the important thing here is that of course what you would expect is that there's kind of an optimal pose ratio, because we just saw that if you pose too far from the manifold, and then you rely on your SBI in extrapolation to denoise too much, this SBI has no transition state knowledge at all, so you could steer away from the transition, which is what we see here for the pose ratio of 1 and 0.75. You need more conversion steps to converge. You also obtain less converged dimer samples, etc., and also less good commuter distributions. But it's also the same problem if you're too close to the manifold, then you don't have enough steps to actually denoise the structure. And so you see that if you're, for example, at point at the 0 level, you basically run into atom colliding problems, and for the 0.25 you get a slightly different worse result to our main result, which is using 0.05. And where 0.0 is basically clean level and 1.0 is the full noise. And on another important consideration is that, well, I told you that we have to compute the scores of SAA at the latent level, but the problem is that we're also computing forces, and the forces there are defined rather crisply on the clean level, and so there is also an inherent discrepancy between the level at which we optimize and either the RSAA direction or the force direction. Because if we optimize at a latent level, then we can estimate the posterior and then estimate the force, which is what we do here. And then if we optimize at the clean level but noise the structure to estimate SAA and then use that direction, regardless of what you do, either way you get a discrepancy. So that's also why you kind of find this optimal pose ratio. But then probably more important thing, the kind of basic thing about the method, if you use it that way, is that you actually get something that converges in all of the metrics. whether that's, just using enough optimization steps and then the behavior converges after some sufficiently, high enough number of steps, or of course you also need a kind of optimal step size, because otherwise you would just wildly oscillate between configurations. So that's like definitive proof that the way we use the SPI and the SAA is actually something that converges to some state. So for the conclusions, so we managed to come up with a method that's CV-free. You have no heuristics, and you can converge to transition states pretty accurately. The main feature is that you capture the diversity, as we saw in the alanine dipeptide example. Even though the transitions are very broadly separated geometrically, because of the broad sampling of SPI, you were able to find all three. And yeah, what's interesting is that we find that both for biomolecular systems and also for chemical reactions. And in terms of perspective, I guess we already talked about that, but yeah, of course, the next thing to do would be on one side to kind of try more broader campaigns with this method using universal MLIPs. So this would with that you would be able to sample transition state for kind of unseen systems. And also one interesting approach is using this kind of method with emulators, like with Boltzmann emulators, because that's essentially the idea, the first idea of training generative model on MD distribution. So with a pre-trained Boltzmann emulator, you would already have this knowledge of the metastable states, and it would make the sampling much easier. And also, again, it will allow you to test the methods in a transferable setting and not a per sample setting. And whether that's in the per sample setting or in the transferable setting, as we discussed, we can think of very easy ways to improve the method, whether that's with faster sampling algorithm or just faster architecture as well. And yeah, thank you to my co-author, so Hyuk-jun, who's the lead on that, Sujing, who's also co-first, and then Miguel for all his guidance on transition state optimizations, and Yangshi and Rafa, of course. And also thanks to Juno for helpful discussion. And thank you guys for your listening. Right, are there any questions?
Yeah, thanks a lot, guys. That was great, very clear. I had a question with still very naive question. It's regarding the use of diffusion. So you're training the diffusion model on points that are close to the initial states, right? And that gives you a score function that you're using outside of these points.
Yeah, so basically you have them I should maybe have introduced the concept of diffusion a bit more, but basically you learning a mapping between a noise distribution and the data distribution, right? And then what you're just learning is how you get from the noise to the data, because then you can just sample the noise distribution, which is easily sampled, and then through the mapping you will effectively sample the data distribution. So essentially you just sample a Gaussian, and then thanks to the model that's able to navigate the SDE and do the mapping between the Gaussian and the data, you effectively sample, by sampling the Gaussian, you sample the data. And so you sample the data here, the data is the MD distribution. So you essentially learn to sample the data distribution that's defined by whatever MD you obtained.
Okay, and then you do that and you use it on regions where you're not in either state.
Yeah, so essentially, yeah, right.
Space where you don't have.
When you sample with the extrapolation of scores, like it drives you to region where like actually there is no data. And what's interesting is that I think what's also happening is that you still get something that's physical, because the like main, like the thing that's like universal in the data, and the first thing that the model will learn is like the bonds and the like typical angles that are allowed, and maybe from some degrees of freedom, the ones that like change them the most, I will be a bit confused. But for the most part, like if you just sample with SBI, you actually get like structural, like physically plausible,
Right.
which is
So then,
remarkable.
like, what happens is that the diffusion model is helping denoise the structure, but then your force field is helping you go in the greatest direction.
So what we do is like several steps here. Like first we like denoise to get samples close to the manifold, because we saw that you have to be close enough to the manifold to do the whole thing. And then from these structure, we stop the diffusion, and now we just use the diffusion scores to like get the reaction coordinate, but we don't denoise. We just move according to this equation. Essentially, we change from denoising with this equation to stopping, and then we still have the diffusion model that's computing something that's useful, which is the difference of scores. And then we optimize, and then we restart the denoising through the SDE.
Okay.
Is that clear?
Yeah.
Okay.
There's one
question. Like, go ahead, Luis.
Oh no, there's a question in the chat.
Oh.
So do you have some elements, opening comments on multi-transition state between A and B? Does ASTRA can work with shallow stable states along multiple step transition? I would say, I mean, chemically, we didn't test that for your second part of the question. I would say in the 2D potential case, which is actually the one here, we saw that we can, like, again, the fact that you sample something that's broad enough, you can like, and also the thing is like the SA optimization is not like strictly bounded by the PS itself. So I would say it has like a bit less of chances to get trapped in like some energy wells. Because it's like the way it's interpolating is like not directly like surfing on the PS. But yeah, I would say we didn't test a specific case for that for chemical system, so I would stay a bit conservative here, and but I would expect that it would work.
Are there cases where you think that NEB can still be more useful than this, or?
Yeah, I mean, I guess like if your degrees of freedom is like very like obvious. For example, like you have ion migration, something that's like a straight channel. You don't need like it's like obvious what's happening. And I mean, then again, we like when you say that, you already know what's the mechanism, so it's biased. So, but like I would say where any transition state method is failing is, let's say you have a complete like a system like for which you like ignore everything, like you don't know anything about it, then you will have to struggle a bit to figure out what are the possible reaction pathways, what are the degrees of freedom, how can you interpolate, because again, when you look at kind of the first figure here, if you do the naive interpolation between the like most stable states, which is what you would do if you didn't know anything about the Nibiru, the system, right? You get like one kind of like one set of paths, which leads you to like a mode collapse onto like one single path, and like some of the other transitions would be much harder to obtain. Again, with the MD based method, I would say it's probably much easier, but then it's also biased because you need to have the right CV. And if you don't get the right CV, it's very hard to converge. So I would say currently most methods are hard to generalize as, you know, like a blind screening method that's working for all systems. And that's kind of the direction towards we try to take a step essentially.
And CV is like
CV is the collective
freedom.
variable. So yeah, you like identify main degrees of, for example, like if it's a SN2 reaction, like it's like you say that the distance between like one carbon and the other carbon, or like whatever is bonding, is like what will make the bond is the CCV. So then you just bias the system to explore these degree of freedom. So like the distance between the things that should form a bond.
That's very clear. In ASTRA, you don't need that because you're noising essentially. It's like you're noising in all coordinates in space, right?
I'm not sure I get your point.
Like when you generate, so when you train your diffusion model, it's like you're noising the stable structures, right? You're just adding random noise everywhere, and then you map.
I would say ASTRA is more. I would say it's more because it's not one of these left ones, like one of these time dependent, but it's time independent, and therefore it's just a time dependent method. So like just optimizing, like because time dependent methods are blindly optimizing. I mean blindly, not blindly, because you hope that the way you describe the PES and get the direction is correct. But it's just that the way you define the coordinates, and this combines with the way you initialize. And because the SAA is robust to like noise things, for example, the NEB in this system, if you interpolate with linear interpolation, it doesn't converge. But if you interpolate linearly and then run ASTRA, it's managed to like converge stuff. Because it's like the SAA itself is not bounded by physics. It will just find whatever direction is what it thinks is the kind of bridging direction between the two states, and then you denoise it anyway.
You're not using collective variable.
Yeah, right. Yeah, but it's more because it's like one of these like time independence methods. But the problem of the time independent methods is that you still need like good guesses, and it's not very robust and stuff. So yeah.
Question.
Yeah, Luis. Yeah.
Maybe I'm biasing myself by your figures and by the comments. Can you go one slide forward, I think? Oh, no, backwards then.
Is it like
on the diffusion? Yeah, that one. So when you, oh no, the previous one, sorry. When you sample here with super diff, this equal density region, it seems to me like it's like your initial guess is somewhere in between the two densities, right? Like that's the whole point, I guess.
Yeah, that's like the whole, like basically our heuristics is there. Is that you expect that when you sample with super diff, you get some kind of intermediate thing. And you would, I think, expect, for example, if you use that with pre-trained Boltzmann emulators, that the intermediate density will be actually way more meaningful, because you would like have a model that's actually normally able to describe the whole PS and not just like isolated states. But then you're using in a transferable setting, so it's still useful to use that, because here we're not in a transferable setting, so we have to like make the lowest assumption possible, which is that you don't know the transition at all. If that makes sense, or maybe I confused you.
Yeah, no, okay. That was pretty much my question, because then I was thinking like, what if your transition stays actually super close to one of the densities? Then your sampling, your initial guess is pretty quote unquote far in that sense.
Yeah, right. That's a good point, right? It depends on how you set the problem, I guess.
Is there a case where a super diff might bias towards like lower energy regions to find the equal density region, or it doesn't matter what the energy barrier is for that?
I think it doesn't matter at all, because the thing is we have equal number of data here and here. So you would, I mean, I guess it maybe depends on how broadly is the data distributed, because then maybe the score signal will be a bit more noisy on one side, and on the other side will be very confident, like go in this direction. But that's kind of superstitious, I guess. But still, yeah, it's like not bounded by the PS at all. It's just like our way of putting some kind of heuristics in there and something like broadly enough. And then SAA is like robust enough to do the rest and just handle the whatever you obtained before. In fact, you can use something else that's then superdiff to sample initial states that will be used to look for TS. Not sure I get the question, but yes, of course, you can use whatever. Like actually, you could use with SAA whatever in like interpolation method you want. But the point is that whatever interpolation is like bounded by, you know, which states do you put on both ends. And you know, again, like when you look at this figure, for example, it's like it can be very sensitive. So the point is that you need something that's kind of like blindly generating something broad enough, but still something that can be used. Yeah, because that's like what we sample with the SBI is like very broad. Here, for example, but the structures still are like kind of meaningful. You know, you don't get completely weird stuff. Okay, yeah, that's
All right. So I think no more questions. Yeah, thanks a lot, Lucas, again. And yeah, we'll just put the recording on YouTube.
Thanks, guys.
Yeah.
Thank you.